Hi everyone, welcome to Multilayer Perceptron. In the previous chapter, we show how you could implement multiclass logistic regression for classifying image of clothing into 10 possible categories. To get there, we had to learn how to rank a data coordinate hour into a valid probability distribution via softmax, how to apply an appropriate loss function, and how to optimize over our parameters. Now that we have covered these preliminaries, we are free to focus our attention on the more exciting enterprise of designing powerful models using deep neural network. Hidden layers. Recall that for linear regression and softmax regression, we map our input directly to our output via single linear transformation if our label really were related to our input data by approximately linear function. Then this approach would be perfect, but linearity is a strong assumption. Linearity implies that for whatever target value we are trying to predict, increasing the value of each of our inputs should either drive the value of the output or drive it down, irrespective of the value of the other input. Sometimes this makes sense. Say, we are trying to predict whether an individual or will not repay a loan. We might reasonably imagine that all else being equal, an applicant with a higher income would be more likely to repay than one with a lower income. In this case, linear model might perform well, and there might even to be hard to beat. But what about classifying image in fashion means? So increasing the intensity of the pieces at location always increase the likelihood that the image depicts a pocketbook. That seems ridiculous because we all know that you cannot make sense out of an image without accounting for the iteration among pieces. Value function, as stated above, the most popular choice due to its simplicity of implementation and inefficiency in training is the rectified linear unit. ReLU provides a very simple non-linear transformation. Given the element z, the function is defined as the maximum of the element and 0. It can be understood that ReLU functions retain only positive element and discard negative element, setting those nodes to 0. To get a better idea of what it looks like, we can plot it. Because it is used so commonly and the array support the ReLU function as a basic native operator, as you can see, the activation function is applied while linear. When the input is a negative, the derivative of a ReLU function is 0. And when the input is positive, the derivative of a ReLU function is 1. Note that the ReLU function is not a differentiable when the input takes the value precisely equal to 0. In this case, we go with the left-hand side derivative and say that derivative is 0 when the input is 0. We can get away with this because the input may never actually be 0. There an adage that is subtle boundary condition matter. We are probably doing real mathematics, not engineering. The conventional wisdom may apply here. See the derivative of the ReLU function plotted below. Note that there are many variants of the ReLU function, such as the parameterized ReLU of ETAL in 2015, this variation adds a linear term to the value, so some information still get through, even when their argument is negative. The reason for using the value is that its derivatives are particularly will behave, other than vanish or they just let the argument through. This makes the optimization better behave if it reduces the issue of the vision finishing gradient problem. Sigmoid function. The sigmoid function transforms its input which take value in RR to the interval 0 and 1. The sigmoid is often called a squashing function. It squashes any input in the range minus INF, INF to some value in the range 0 and 1. In the earliest neural network, scientists were interested in the modeling biological neutron which either fire or don't fire. Thus, the pioneer of this field, going all the way back to Max Truland and Pick in the 1940, a focused thresholding unit. A thresholding function takes either value 0, 0. If the input below the threshold or value 11, if the input exceeds the threshold, when attention shifted to gradient-based learning, the sigmoid function was a natural choice because it is a smooth, differentiable approximation to a thresholding unit. Sigmoid are still common as a deviation function on the output units. When we want to interpret the outputs as probability or for binary classification problem, we can think of the sigmoid and as a special case of the software, but the sigmoid has mostly been replaced by the simpler and easier to train ReLU for the most used in hidden layer. In a recurrent neural network chapter, we will describe how sigmoid unit can be used to control the flow of information in a neural network thanks to its capacity to transform the value range between 0 and 1. See the sigmoid function plotted below. When the input close to 0, the sigmoid function processes a linear transformation. The derivative of sigmoid function is given by the following equation. The derivative of a sigmoid function is plotted below. Note that when the input is 0, the derivative of the sigmoid function reaches a maximum of 0.25. As the input diverges from 0 to either direction, the derivative approaches 0. Time function. The sigmoid function, the hyperbolic tangent function as stresses its input, transform them into elements on the interval between -1 and 1. We plot the time function below. Note that as an input near 0, the time function approves a linear transformation. Although the shape of the function is similar to the sigmoid function, the time function exhibits point symmetry about the origin of the coordinate system. The derivative of the time function is the derivative of time function is plotted below. As the input nears 0, the derivative of the time function approves a maximum of 1, and as we saw with the sigmoid function, as the input moves away from 0 in either direction, the derivative of the time function approaches 0. Thank you.